Hi, I'm Michael Pfeifer. This is another episode of Metal Conversations. Every once in a while, I notice a company's website uses the term Six Sigma to convey good quality. And when I see this, I wonder if they really understand what Six Sigma is and what it applies to. I used to work in a manufacturing production line when I first started working. It was at Motorola, who was one of the first adopters of something called statistical process control. And statistical process control is a data-driven methodology that's used to monitor and control a manufacturing process. It's actually also used for other processes, but I'll be focusing on manufacturing processes. The goal of statistical process control is to produce output from the manufacturing line that meets customer requirements, and also to maintain variations in the output from the manufacturing line within acceptable limits and to minimize defects. And we can apply statistical process control to any process with output that can be measured, producing parts where we can measure the dimensions or measure properties such as tensile strength, yield strength, or electrical resistance or electrical conductivity. Weight is another one. For any process where the output can be measured, we can use this statistical process control. So the attributes of the process output are measured, collected, and analyzed, and the data is used to identify and eliminate causes of process output variation and also to make process improvements that improve the quality of the process output. Several calculations are involved with statistical process control, and one of the calculations that's made is in the standard deviation, which is also referred to as sigma. So standard deviation is a calculated value that describes the spread of the data in a data set. The larger the standard deviation is, the larger the spread in the data and the more variation there is in the data, which indicates that there's variations in either the input materials that are used to fabricate the components or make an assembly, or in the process used to fabricate a component or assembly. So with statistical process control, the standard deviation, or sigma, is continuously calculated for the data collected, and then the standard deviation is compared to the limits, the specification limits for the output variable that's being measured. So for measuring, let's say, the dimensions, there will be an upper and lower limit for, let's say, how long a component can be or how wide it can be, or an upper and a lower limit on the material's strength or its electrical conductivity, and so on. What we want is to have the standard deviation be as small as possible, which indicates a small variation in the output being created. Now, where Six Sigma comes in is if we take the average of the data that's collected and add 6 times sigma to the average, and also subtract 6 times sigma from the average, that total range from minus 6 sigma all the way to plus 6 sigma from the average, if that range is within the upper and lower limits for the thing being measured, then we have a Six Sigma process. And what it indicates also is that only 3.4 parts out of a million are going to be defects. That is the origin of Six Sigma, but it's really related to statistical process control. What I want to talk about in more detail is how materials engineering fits in with statistical process control. So materials are used to fabricate components and join components together. And we want manufacturing processes that are capable of producing components and assemblies that use materials that have the desired properties. So developing and maintaining a Six Sigma manufacturing process depends heavily on materials engineering. That is, engineering the materials that are used in the process and engineering the process so that it causes the desired changes to the materials in order to produce output that meets our requirements. So there are a number of different ways where materials engineering fits in. The first is selecting materials that have the composition and the properties that are compatible with the process, enabling good manufacturability. Not all materials are good materials to use with specific manufacturing processes. For example, some steels are easier to machine than other steels. For example, a 1045 steel is okay to machine, but if you add if you add sulfur to it or lead to it, then it becomes really easy to machine. So a leaded 1045 steel is a lot easier to machine than a non-leaded 1045 steel. But there are certain things we can't do with the steel after machining it if we add lead to it. Some metals are easier to stamp and form than other metals, and some metals are easier to weld than other metals. And so selecting the materials that are appropriate for a particular manufacturing process is important for helping to get good manufacturability and having good manufacturing output. And sometimes people will select materials that aren't so easy to use in manufacturing, and they end up causing problems. Either there'll be scrap, or it would have to be rework of the thing being made because the material isn't ideal to work with. The next thing is characterizing the effects of the incoming materials variations on the process output. When we buy materials from a supplier, such as, let's say, steel bar or brass sheet, or any other material or metal, there will be variations in that material. They can't make the material with the same composition and the same properties over and over again. There will be some spread in those materials. It's important to understand what is that expected variation that we're going to get from any particular supplier, and how will that variation in composition or certain properties of the incoming materials affect the output. And so doing that characterization is important, and that involves, again, materials engineering. Then we want to control the composition and the properties variations of the incoming materials and make sure that the materials are held within a certain amount of variation. Now, some processes might be capable of withstanding a large variation in the composition and other properties, and other processes might not. Regardless, we have to understand that and then select suppliers that are capable of providing materials that consistently are within the variation that we need. We have to write good materials specifications that clearly state what the allowed variations are in the materials. And then we have to verify that suppliers are capable of supplying the materials or components that meet specifications. So we want to reduce the variation of incoming materials because the materials can affect the output. And quite often, issues with incoming materials cause problems in the output. This control over the composition and properties of incoming materials and verifying that suppliers are capable of supplying the materials and components that meet specifications means evaluating them and understanding what their manufacturing capabilities are, whether their processes are Six Sigma, and also whether they have the technical capability and understanding of what they're doing to be able to fix their processes if there are problems, and also if they understand what the needs are for the materials that they're supplying to you. If they don't have the technical capability and they don't understand the process, then you can expect unexpected variation in what they supply, and you shouldn't be surprised when there's a problem. Finally, we want to use failure analysis to help identify the root cause of quality problems that lead to scrap or rework. When there's a problem with manufacturing lines, we need information about the materials involved. Are the incoming materials meeting specification? What's going on with the output materials? What is the problem with them? We need to perform analyses on both the incoming materials and the output materials to understand what's going on. We evaluating the composition, the microstructure, the properties that are important for that particular process. With that information, we can determine, is it a supplier problem or is it a problem with a certain step in the manufacturing process? And don't always assume it's a supplier quality problems. A lot of times that's the first reaction that people have. And as an example, I worked on a problem where a company was having problems stamping sheet metal. It was stainless steel, where they were getting cracks in the components that they were fabricating. And we evaluated samples from both a good lot of material and a supposed bad lot of material, and found that they had exactly the same composition, the same tensile properties, the same microstructure. And what that indicated is that there was a problem with their manufacturing process, that something had gone wrong. But that information pointed them back in that direction, and they were able then to identify the problem with their process and fix it. So statistical process control is a powerful tool for improving quality, reducing costs, and increasing customer satisfaction. Coupled with engineering the materials, that is material selection, writing good specifications, evaluating suppliers, using failure analysis, we can develop capable processes that continuously produce output that meet our requirements. As with anything else like this, if it was easy to do, everyone would be doing it. But it requires a commitment from management and employees to be successful, And it takes engineering focus and discipline to collect and use the data to make process and design improvements. So that's it for my discussion about Six Sigma and statistical process control and materials engineering. If you're interested in learning more, I recorded the video and wrote an article that goes into more detail about statistical process control and standard deviation. It's on our website in one of the recent blogs. Our website is www.imetllc.com. If you're interested in hearing more and learning more, sign up to receive our podcasts or to receive emails about our webinars, new articles and courses. And that's it. So thanks for listening. Good luck with your metals. Bye.